So before doing that, I will finish the last class that I was talking about derived functors, right? So something that I didn't prove is the following lemma. Okay, so let alpha dot be a quasi-isomorphism and ik be an injective object for every k. Then the k-derived functor, k-derived object of a dot is isomorphic to the k cohomology of I dot after applying f. Right? Okay, so how's the proof of this lemma? So consider any, so let beta dot from A dot into J dot be any quasi-isomorphism such that it satisfies all the properties of the definition of the derived of the k-derived object, so such that these guys are injective for every k, and this map is injective, is a monomorphism. Okay, so we know by the first lemma that I stated in the last class. So by lemma 1, we know that there exists a quasi-isomorphism so let's say phi from J dot to I dot such that, well, we have the following diagram, right? The commutative diagram is A dot, it's like this. So, right? So now we will construct the cone of this quasi-isomorphism. So it is Ck, that it's defined as Jk plus Ik minus 1. And we will define the dc to be dc. It will be, well, dck. It will be dckj 0 minus 1 to the k phi k and d k minus 1 I. Sorry. right? So we define it like this. Okay, so it's clear that it is a complex, right? DC composed with DC is 0. And furthermore, it's not just a complex, it's an exact sequence. Okay. Furthermore, C DC is exact. Okay, let's prove that. So in fact, take any element that goes to 0, right? So if dk C of jk ik minus 1 is 0, this is the same as saying that dkj of jk is 0, and phi k of jk is equal to minus 1 to the k minus 1 of dk minus 1 ik minus 1, right? So since phi dot is a quasi-isomorphism, okay, so we're saying here that jk is a closed element, that its image under phi, it's exact, right? So in cohomology, its image will be 0, right? So since phi dot is a quasi-isomorphism, we know that jk must come from something exact, right? So we know that the class of jk must be 0. So jk is equal to dk minus 1j of some jk minus 1, right? So let's, so in particular, we have that this dk minus 1I of the following thing of phi k minus 1 jk minus 1 plus minus 1 to the k I k minus 1 is equal to what? So it will be, after commuting the d with phi, you will get phi k j k plus minus 1 to the k of d of ik minus 1, right? Of di k minus 1, ik minus 1, and this is 0. Right, so this means that this element is closed, right? This is a closed element in the complex J dot, right? And so since phi dot is a quasi-isomorphism, it must come, its class must come from some class in I dot, right? So again, since phi dot is a quasi-isomorphism, we know that there exists some, let's say, j tilde k minus 1 such that it is closed. right? And its image is equal to the class of this guy up to something exact, right? So jk, so phi k minus 1 of jk minus 1 must be equal to this element phi k minus 1 jk minus 1 plus minus 1 to the k I k minus 1 plus something exact, right? Plus d k minus 2 I of I k minus 2. Right? Okay, and so we are done. I mean, this means that jk ik minus 1 is equal to d k minus 1c of the following thing. So it will be j k minus 1 plus minus 1 to the k minus 1 j tilde k minus 1 and minus I k minus 2. Okay? So it is exact, right? Okay, so now, okay, we know that so since C dot, let's say CK, are injective for all k, and C dot is exact, right? So this complex is quasi-isomorphic to the zero complex, right? So then it is quasi-isomorphic to the zero complex. Right, and so the identity is homotopic to the zero map, right? And so when you apply f to this is homotopic to 0, right? And so all the cohomologies are 0. I mean, this so the HK right? Then so now since by the construction of C dot is a direct sum of these guys. So since we have the split short exact sequence, so it goes from 0, I don't know, I dot minus 1, C dot, J dot 0. It will remain exact after applying f. So f I dot minus 1, f of C dot, f of J dot is also exact. and split, right? Well, and so we're done. I mean, then taking the long exact sequence in homology, we get the desired isomorphism, right? We get that HK of f of j dot is isomorphic to HK plus 1 of f of I dot minus 1, that is HK of f I dot. Right, and this is by definition the kth derived object of f of A dot. Okay, so this is the proof of the lemma that I didn't prove in the last class. Now I will do just a final proposition about these derived factors. So the final thing that I want to do is the following. So proposition. So let given any short exact sequence of complexes in an abelian category, A with enough injectives, so it has associated a long exact sequence in derived objects, right? So and if a left exact functor, covariant functor, we have a long exact sequence, derived long exact sequence. This is the what was that? Okay, so it's okay, so how's the proof of this proposition? So in order to prove it, well, first of all, I have to put another lemma. So lemma. So given a short exact sequence of complexes, say 0, A dot, B dot, C dot 0, there exists a short exact sequence of complexes of injective elements extending it. So we have this 0, A dot, B dot, C dot 0 inside I dot 0, J dot, K dot 0. Right, and so in fact we can take it split. Okay. So maybe I will put it here. Okay, so the proof of this lemma is quite simple. So take any extension of B, let's say beta, by injectives, any extension of C, I don't know, what's the letter used? K. Gamma K, so by complexes of injectives. We already know how to do that. And then consider the following diagram. So take no, I have to put names to these maps. Okay, so let's put a name for alpha, beta. Okay, so okay, so I mean, okay, let's say this is phi, this is psi, right? And this is beta. This is psi, k dot 0, and here you take I dot plus k dot, the second projection, and so what should I do? I have to put here psi, I mean phi, plus this composition, right? Psi composed with beta. Okay, so we have this diagram. This diagram is commutative, and so we just have to take the kernels here and we're done, right? Right? Fine? Yes? Okay, so using this lemma, we can produce, this lemma says that we can extend by injectives short exact sequences of complexes, right? So we can produce like injective resolutions of short exact sequence of complexes, right? So proof of the proposition. So take this short exact sequence and consider a double complex, short exact sequence of double complex, right? Consider a short exact sequence of double complexes so we have here 0, A dot, B dot, C dot 0, and here we have I dot dot, J dot dot, and K dot dot, right? In fact, we can take this short exact sequence to be split. right? And we know that they are injective resolutions at every p, for every p, right? So such that they are injective resolutions at every p. So again, by what we saw the last class, we have now a short exact sequence of simple complexes associated to these double complexes. And these maps, these injective maps, are now quasi-isomorphisms, right? So these maps now are quasi-isomorphisms. And well, and we're done. I mean, since we know that this short exact sequence is split, or if we apply the corollary that we obtained at the end of the last class, we know that this short exact, well, the short sequence of complexes remains exact after applying f, right? This is exact. And so the long exact sequence, the desired long exact sequence, is obtained from this, right? Right? Okay. Okay, so now I will change. Well, I will focus on a particular category, that is the category of abelian shifts over some topological space. So in order to apply all this machinery to this category, well, I won't prove that it is an abelian category. I will assume that you already know that. So what I will do is to prove that it is a abelian category with enough injectives, right? So before doing that, proposition, I will prove that the category of abelian groups has enough injectives. So the category of abelian groups has enough injectives. And furthermore, we can characterize the injectives abelian groups. They will be the divisible groups. So proof. So let's. Okay, so let us check first. First, that every that the injectives are the divisible groups. Okay, so in one direction, so if G is injective and G is any element of G, we know that we can define a map from Z to G that just takes 1 to G here, right? And then we have this multiplication by n injection. And so since it's injective, we know we can factor this, right? So if we take this map to be, let's say, phi, then G will be equal to phi of n, that's equal to n times phi of 1, right? So G is divisible. And conversely, and given G a divisible group, so we have to show that it is injective. So take any homomorphism. So something from G to, let's say, to A to G, and an extension of A, B, and we have to produce this map, right? So what will we do? We will consider a maximal extension, right? We know by Zorn's lemma that there exists a maximal extension. So suppose that we have here B prime, B, and we have here a maximal extension. Okay, so if B prime is not all B, there exists some B that it's in B minus B prime. And well, let's call this map psi. Then so consider the following idea: I to be all the integers such that n times B belongs to B prime, right? This is an ideal inside Z, so it is generated by some integer m, right? And we know then that m times B belongs to B prime, so it has an image. Now just take any G in G such that psi of m times B is equal to m times G, right? And then extend psi of B defined to be G. This is well defined, this is an extension, and so you will get a contradiction, and this implies that B prime is equal to B, and then G is injective. Okay, so how do we prove now that every abelian group can be injected into some injective abelian group, or in some divisible abelian group? Just take G and take the following map to the home of the home from G to Q over Z to Q over Z, right? And this is the B dual of the group G, and the map is just taking G and take it to the map that takes a homomorphism, let's say F, and take it to F of G. right? And this map, so this map is injective. Why it is injective? So if G is non-zero, this implies that the cyclic loop generated by G is non-zero. And so we can construct a non-zero map, F0, to Q over Z from this to this. So since Q over Z is obviously divisible, it is injective, right? So we can extend this map to a map from G to Q over Z, right? And, well, this map will be non-zero. And obviously, when you apply it to G, it will give you f of 0 of G that it's non-zero, right? So f of G is equal to f0 of G, that it's non-zero, right? So this map is injective, and obviously, since Q over Z is divisible, this group of homomorphisms will also be divisible, right? And this is right. So this is the proof. Okay. So using this fact, we can now prove that the category of sheaves of abelian groups over a topological space is has enough injectives. So corollary, the category of sheaves of abelian groups over a topological space X has enough injectives. And the proof is quite simple. So take any sheaf of abelian groups F. Then you look at for every X in X. So you know that F can be identified with a subsheaf of the sheaf of total discontinuous sections of this, right? Let's say right where this J takes the point and inject it into X. Right, so we know that it's a subsheaf of this very big sheaf, and then extend every fx inside some ix by injectives, and then this will be inside this big sheaf I, that is just the product of these injective sheaves, right? And this will be obviously injective, right? I mean, to define a morphism to this sheaf from any other sheaf, when you think on the sheaves as the continuous sections of the Thal space, the only thing that you have to do is to define it point-wisely, right? So point-wisely, you will have, if you have any morphism of some sheaf to I, it will be equivalent to give a collection of morphisms from the stalks of these sheaves to the IX, and each of these collection you can extend it, right? And we'll give you another collection of morphisms that will be the same thing as giving a map from the extension of the sheaf to I, right? So this is injective. Okay. Well, so a remark is that given any short exact sequence of sheaves, zero F G H we have a left exact sequence, right, in global sections. We have an exact sequence. Zero, f of x, g of x, h of x, and this last map is not necessarily surjective, right? So, so in other words, the global sections functor gamma that goes from the category of sheaves to the category of abelian groups is left exact. Okay, so we can define the sheaf cohomology. So definition. Let X be a topological space. We define the sheaf cohomology groups of X with coefficients in some sheaf G. I mean F. As hk of x with coefficients in F, it is defined as the k-derived functor of the global section functor of F. Okay. So from what we already know from the last class, so we know the following thing. We know, so proposition. So if F dot is a gamma cyclic resolution of F, then we can compute the sheaf cohomology of F as the cohomology of the global sections of this resolution, right? So we know this, and we already, from what I already did, so if we have any short exact sequence of sheaves, there exists a long exact sequence in sheaf cohomology, right? So we have this. Right. Well, what else? We know that the H0 is the global section functor. Okay, so we produced a way to complete this sequence, this short exact sequence when we apply the global sections functor, right? These are exactly the sheaf cohomology groups. Okay. So what time is it? What will I do now? Okay, so now I will explain how do we compute these groups in a concrete way. So this is the check cohomology. So definition. Let X be a topological space. Let U, UI, I in I be an open covering of X. Okay. So we define the groups of check cochains with respect to U. Right? And with coefficients in some sheaf. So it's CK of U F. It's by definition the set of sigma that belong to the product I into I to the k plus 1 of F of U I0 IK such that sigma is alternating in I, equal to in the coordinates of I. Okay, so in particular, if we order this index set of the covering, so if we put a linear order on E, on I, we can identify CK U F with the product of I0 less or equal than IK of F of U I0 up to IK, where this U I0 IK denotes the intersection. Okay, now we define the check differential operator delta that goes from CK U F to CK plus 1 U of F. And we'll take any sigma here and we'll leave it to some delta sigma that in the coordinates I0 IK plus 1, it's by definition the sum from L equal to 0 up to k plus 1 minus 1 to the L sigma of here I0, you remove IL up to IK plus 1, okay? And it's routine to check that this gives you a complex. Okay, so this is the check complex associated to the covering U with coefficients in the sheaf F. And so we obtain the check homology groups. So the check cohomology groups with respect to U. So we will denote them like this: HK check of U with coefficients in F. They are by definition the cohomology associated to this complex. right? So here a remark. So using the definition of the properties that define a, using the properties that define a sheaf, you can prove that for any covering, the H0 check corresponds to the global sections of F, right? They are collections of sections such that in the intersection they agree. So these are the global sections. Okay. Well, furthermore, this check homology groups and these check cochains, in fact, they define a sheaf over F, over X, a sheaf of Abelian group. So in fact, so if we let any F, any sheaf over X, so we can define for every covering so we can define for every B contained in X open, we define the covering U intersected with B at the covering given by the intersections of the covering with B. So this is a covering of B, right? Okay, and so the restriction maps so for every pair of open sets, let's say B containing U open, we have the restriction maps from U to B, and they define restriction morphisms from C dot U cap B F to C dot U cap. Which one? Right. That is. This is just a product of copies of F restricted to some intersections relative to the covering U. So obviously the restrictions will define this restriction map here, right? And this defines a sheaf that I will denote it like this: C dot U of F underline of abelian groups over X, and obviously the global sections of this sheaf correspond exactly to the check cochains associated to U with coefficients in F, right? And again, since these restriction maps clearly they commute with delta, so since the restrictions of C commute with the check differential, we have in fact that the check differential, it's a morphism of sheaves. So we have the check complex of sheaves so it comes from, so we have 0 C0 U of F delta C1 UF, delta C2 UF, and so on. Okay. Okay. Everything clear? Okay, so the proposition now is that this complex is in fact a resolution of the sheaf F. So where is this? I cannot find it. So here, proposition. So the check complex is a resolution of F. So proof. So we have to prove that this complex is in fact exact, right? So we have to, and this is a complex of sheaves. It is enough to check that for some open neighborhood of any point, it remains exact, right? So in order, so it is enough to check. Well, that this is exact for some, so for every x in x, it is enough to check that this is exact. X in x, there exists some b neighborhood such that this remains exact in B, right? So it's like this. Okay. Okay, how do we prove this? So for every x in x, okay. So suppose I don't know how to write this. So assume x belongs to some ui, okay, for some I and I. Okay, so and take B equal to UI or B contained in UI, right? Okay. So I want to prove that this is exact for this B. So let's prove that. So take any sigma that is in the kernel of this map, of the delta map, right? That goes from ck of u intersected with b, f to ck plus 1. Okay, and so we know that sigma in the coordinates I0, ik restricted to ui intersected with I0, ik intersected with B, right? This will be equal to, I'm applying delta to sigma. This will be equal to the sum of L equal to 0 up to K of -1 to the L sigma, and here I am taking I0, IL, IK, restricted to this thing, same thing, UI, UI0, UK, B. Right? This is just because it is delta of this thing is 0. Right? That's the equation. And this is for any, for I, well, this I. Okay, and we know that this is equal to this. This is I0, IK intersected with B, right? Because B is contained in UI. And so now the only thing that you have to do is to take tau, right? Tau will be an element of CK minus 1 of U intersected with BF given by tau of I1 up to IK. It's by definition sigma I1 up to IK. Okay, and this is obviously well defined, right? Because every intersection that you will take will be inside UI, so sigma I is in fact an element of F of U I1 IK intersected with B. And obviously the delta of this tau will be sigma, right? This is exactly what this equation is saying. This will be delta of tau, right? Okay, so this implies that this sequence remains exact, and so the sequence of sheaves is exact, and well, up to and it's a resolution of the kernel of this map, and obviously the kernel of this map is F. Just because of F being a sheaf, right? Okay, so I will. Okay, is it clear? Yes? Good. Okay, so now I will prove a theorem. What time is it? I still have time. So theorem. This is Lerais theorem. So let X be a topological space. F a sheaf over X, and U be an open covering such that all the cohomology, the sheaf cohomology groups of the intersections of F are 0 for every I0 and for every Q bigger than 0. Right? So I'm saying that the restriction of F to each of these intersections is acyclic, gamma acyclic. Then the sheaf cohomology is isomorphic to the check cohomology So this is telling us how to compute the Schiff cohomology group. The only thing that you have to do is to find this good covering where all the restrictions of the Schiff remain acyclic, and then you will be able to compute it using these Čech cohomology groups that are explicit. So the proof is quite simple. We already proved. So we know that the Čech complex is a resolution of F.
Excuse me, do we have to suppose that the covering is locally finite also?
Locally finite?
Yeah.
Locally finite? No. Locally finite? No. No, I think no. No. Okay, so we know that this is a resolution, and the only thing that we have to prove now is that this is a gamma cyclic resolution, right? If we prove that this resolution is acyclic, we already know that the derived functors can be computed via the cohomology of the functor applied to this, right? And it will be exactly the Čech cohomology, right? So it is enough to note that this Schiffs, in fact, so that this Schiff is in fact a product, right? And the hypothesis is saying that these guys are gamma cyclic. That's the hypothesis of the theorem. So this product is gamma cyclic. And we're done, right? This is gamma cyclic by hypothesis. Okay? Okay, so what time is it? Okay, now I will give you another property of these Čech cohomology groups. So even though that you don't have this property, this good property of the covering, I mean this good property that all these restrictions are acyclic, with less hypothesis you can have a long exact sequence in Čech cohomology. So at X, a topological space, and consider a short exact sequence of shifts. So we have here 0, F, G, H, such that only the H1 and let U equal to the UI, I and I, be an open covering such that only the H1 is 0. Of F. And then you have a long exact sequence in Čech cohomology. Okay, and the proof, well, in the case that the cover is a good covering, this is obvious. This is just the long exact sequence given by the chief cohomology, right? But when you don't have that, the proof is is simpler, and it's good to do this proof because it's constructive, right? So the proof is so by hypothesis, the short exact sequence remains exact when you in global sections, right? This is exactly the hypothesis. Right, the only thing that you have to check is that the first cohomology of this group restricted to the intersections is 0. And so you have the short exact sequence of complexes of check cochains, and the sequence follows taking the long exact sequence associated to this short exact sequence of complexes. Okay. Right? Okay, so what's the important thing? The important thing is this construction of the long exact sequence is constructive, right? You're just using the snake lemma to construct it, right? So the coboundary map here is explicit. Okay? So the point is that whenever you try to construct this long exact sequence for any short exact sequence of sheets in check homology, you will see that if you don't have this restriction, you won't be able to construct the coboundary map. And what you will be able to do is to construct a coboundary map up to some refinement. Okay, that's the point. So, in fact, you will be able to produce some kind of coboundary map whenever you admit refinements of open coverings. Okay, so first I have a mess here. Okay. So the remark is like this. So the remark, so in general, we cannot produce the long exact sequence. So since we cannot assure that this map is surjective, right? That's CK from G to CK of G. Well, in general, this map is not surjective, right? So in fact, given some sigma that is in CK of UH, we can construct using the same coboundary map that gives you the proof gives you. So we can construct some tau. Well, no, it's not using the command remember. It's just using the surjectivity of the shift, right? Of the shift morphisms. So here's tau of g, such that, I don't know, let's put a name for this pi. Let's say pi u. So such that pi v of tau is equal to the restriction from u to v of sigma, right? Where this v say equal to vj, j in j, is a refinement of u. And what do I mean by this? This means that there exists a map T that goes from j to I, such that u of t of j is contained in bj. No, it's the other way. So it's from j to I or from I to j? Such that bj is contained in u of t of j for every j in j. Right, and this restriction map of coverings, right? Rho ub of sigma, whenever you apply to j 0 up to jk, is the same thing as sigma of t j0 t jk restricted to okay, so this is the map. So this is what you're able to do, right? And so you have these restrictions, right? Rho ub that are going from word to word, from c dot uf right? Well, it's not f, I think it's g. It's h. Right, and furthermore, you can prove that these restrictions morphism, they induce a morphism in check homology, right? So, and they obviously commute with delta, and so they induce like restriction morphisms. Like this, and furthermore, you can prove that this map are independent of the choice of the refinement. So it doesn't depend on the choice of t, and so you have a collection of morphisms that is depending only on the relation of being a refinement, right? Not in which refinement you're taking. Okay. So we have a directed system. So we have a direct system. And we can define the check homology now independent of the covering. To be the direct limit, right? Okay, so now it's an exercise to take the definition of the coboundary map that you obtained from this proposition and to construct it for these check homology groups for the direct limits and to check that it is exact. I mean, you can do it by hand, right? So you have proposition given a short exact sequence of shifts, there exists a long exact sequence in check homology, but now independent of the covering, right? So the proof is an exercise. Okay, so now, I don't know what time is it. Maybe the last minute? No, I have more time. Okay, so what I want to prove now is that these check homology groups are in fact isomorphic to the chief homology groups. Now, I mean, they are always isomorphic, right? This is independent of the covering, right? So, so in order to prove this, I have to introduce another concept, so definition. We say that a sheaf F is flabby if the restriction maps are surjective for every U open. Okay, this is a flabby sheaf. So a remark is that by the construction that we did, so remark every sheaf admits a flabby injective resolution. Right? Just remember that that I injected the sheaf in something like this, right? And this is obviously flabby, right? Because this is the sheaf of all discontinuous sections of this thing, right? So obviously you can restrict, I mean, you can extend everything by 0 outside the point, right? Okay, so proposition. Let F be a flabby sheaf. U be any. Here I don't know if I needed it to be locally finite or what. 1 second. Well, I don't know here if I need it to be locally finite. I will just put any open covering. Then the kth cohomology groups of U are 0 for every k. What time is it? Well, maybe I will leave this as an exercise. This is constructive. I mean, you construct, in fact, given any element that delta of this thing in check homology is 0, you can construct the other guy, and so the proof is I mean, the hint of the proof is constructed explicitly for a finite covering. And then, well, for the general covering, you have to use transfinite induction. Okay, so in the last, well, this I will leave it as an exercise. Maybe we will do it in the exercise session. So last part, theorem. So the check cohomology is isomorphic to the chief cohomology. Okay, proof. So let F inside some I with I flabby and injective, and let G be the quotient, right? Right. So we will prove it by induction on K. So this is for every K. So by induction, K equal to 0 is obvious, right? K equal to 0, the H0, and this is equal to the H0 for every covering, right? Is F of x, and it's the H0 of x. Now for the inductive step, since you already have this this property that the flabby shifts are the check cohomology with respect to any covering, well, are 0. So in general, well, here I'm not sure. Maybe for the proof of this, I mean, in order to do the transfinite induction, maybe you will need that it's locally finite. I'm not sure. Maybe this is true just for paracompact topological space or something like that. I'm not sure. Well, so for k bigger than 0, what you will have is if you take the long XX sequence, you will get that. So here you have HK HK minus 1 of x with check with coefficients in I. Here you have HK minus 1 of x with coefficients in G, HK of x with coefficients in F, HK of x with coefficients in I, right? And here you have a natural map, right? That goes from the check cohomology to the chief cohomology. And how is this map? So the point is that if you take any injective resolution of your chief F, or any, for instance, how is this map? So if you take any injective resolution of F, and then you also have the check resolution of of f, right? So you have the two resolutions. I don't know. For every open covering here, right? And so by the lemma 1 of the last class, we know that we have here a natural morphism of complexes that is unique up to homotopy. And it will define the map that goes from the Check homology with respect to U. And again, using the same lemma, you can prove that this morphism is commutes with the refinements. And so you will get, at the limit, a natural map here. And this natural map, you can also prove that it commutes with the long exact sequence using the same lemma. Okay. Well, and here you're done. I mean, this we already proved it. They are all 0. And well, and so this follows by induction. This is induction. And so by the 5 lemma, this implies that this is also right. Okay. Well, next class, I will continue talking a little bit about well, and a corollary of this. Corollary is that the Flaby shifts are gamma cyclic, right? Okay. Do you have questions?